So I'm going to show you how to arrive at 6 Maclaurin series that you must know. Pretty much memorize the infinite series form. So we're going to try to build up to that point where we can find an infinite series of a function. So the way we are going to do that is using the Maclaurin formula, I guess, if you want to think of it like that, where it's the infinite series from n equals 0 to infinity of the nth derivative of f evaluated at 0 divided by n factorial and times x to the n. If you're not familiar with this formula, I have a video that talks about this formula and why it's written in this way. Why is it like n factorial? Why is it derivatives and why is that 0? So if you don't really know too much, I would just suggest look at that video before you look at this. Otherwise, there's no use in this video because you're just going to blindly apply a random formula you have no idea about. So this is the formula we're going to use because this is the Maclaurin series formula. And we're going to apply it to 6 different functions and arrive at expressions that are kind of similar to this. So let's begin with the first one. I'm going to do each of them in a different color. So the very first one is 1 divided by 1 minus x. Okay, let me scroll down from here. Let's just show the Maclaurin series at the top. We have this, and we have this. So typically the process is find the first couple terms, and then you'll see a pattern emerge. So let's do that. So given that this is f of x, we want to start finding the numerical, or not the numerical, the nth derivative, and then we want to evaluate the nth derivative at 0. So I'm going to make 2 columns. Actually, I guess 3, because we're going to keep track of n. I'm just going to go all the way to 3. And maybe a pattern will emerge after 3. So let's begin. We have the nth derivative, or the 0th derivative of this function, which is itself. And then we plug in 0, we get 1 over 1, which is 1. Okay, that one was easy. The derivative of this function is 1 divided by 1 minus x squared. And I'm going quickly into derivatives. If you really wanted to, you can do them yourself. But this is just the derivative of this function. And this is equal to, let's see, if we plug in once, 1. Okay, easy. Now the derivative, the second derivative is, let's see, it's minus 2, but times negative. So it's 2 over 1 minus x cubed. And if we plug 1 in, we get 2. And then if we do the next one, 3 would be minus 3 times 2 times negative 1, and then raise it to the 4th power. So it's going to be this. I'm just doing the derivatives quickly, but again, take your time with this, especially if you're doing it on your own. So then if I plug in 1, I get 6. Okay. Another way we can write these numbers, actually, is 0 factorial, 1 factorial, 2 factorial, and 3 factorial. We'll see exactly why I wrote it like this when we get to the Maclaurin part of it. So now we just fill it into the formula. Let's go to infinity, and then we just fill it into this. This is the formula you must know, and with this formula, you can get to every single function you want. So now let me just write out the first couple terms. So f of 0 divided by 0 factorial times x to the 0 plus f of 1, or not f of 1, the first derivative, so at point 0, divided by 1 factorial plus the second derivative evaluated at 0 divided by 2 factorial x squared. I've got an x on the first term. And then the 3, this is 0, and then that. Okay, so now let's just fill it in. So f of 0, we found in this table, is just 0 factorial divided by 0 factorial x to the 0. Okay, easy. This one right here, f of 1, this is 1 factorial divided by 1 factorial times x. So yeah, let me just show it's equal right here. It's equal to this plus that, plus 2 factorial divided by 2 factorial times x squared, plus 3 factorial divided by 3 factorial times x cubed. And we see the pattern starts emerging. If you were to guess, the next term would be 4 factorial divided by 4 factorial x to the 4th. And then the next term would be 5 factorial divided by 5 factorial x to the 5th. And you can actually prove this by continuing this down, but I'm not going to do that out of time's sake. So now we have this thing. Now we want to transition this by simplifying it through. So x to the 0 times 1. Remember, 0 factorial is 1, not 0. So 1, this is the first term. It's going to be 1 plus, so we're done with this term. This is 1 divided by 1 times x, which is x. This is 1 times x squared, and then 1 times x cubed, and then x4, and then x5. x5. And we see that the pattern will just continue on like this, x6, x7, x8. So how do we represent the nth term? So if this is the 0th term and this is the 1th term, we're kind of straying away from this n. We're talking about a different n. The nth term is ... n equals n, or just any number, is x to the n. With that, we can write the infinite series of this function. The infinite series from n equals 0 to infinity is, in fact, 1 over x to the n, which is equal to this, but then we have to look at the convergence interval. This is a type of power series, so it can only be looking at r, so r is x in this case, so if r is x, x has to be, or the absolute value of x has to be less than 1, so that's the interval we're looking at. So I'm going to write that condition here for x is less than 1, and that's our first Taylor series you must know. Here's it all in all the work shown. Let's move on to number 2. Number 2, let me zoom in now. Let's see, there we go. Number 2 is e to the x. E to the x. Okay, what's the Taylor series expansion for this, or the Maclaurin series? So it's going to look like this, divided by n factorial x to the n. If you write it out every time before you do it, you'll memorize this equation much faster. So here we have it. So n, I'm going to keep a chart for f of this, and then I'm going to keep a chart of that. So let's see, 0, the derivative, or it's going to be a plain simple form, and it's going to be 1. Okay, very simple. 1 is going to be e to the x, and then evaluate it as 0, you get 1, 2, and you're still going to get 1. And this pattern of 1s will keep going forever because the derivative of e to the x is itself. So let me just write the first couple terms. And maybe you can already speed ahead of me at this point if you already know what you're doing. Just check back at the end to make sure you got the correct result. 1 factorial. Let me zoom out so I can write a bit more. Okay, I guess there, that's fine. X to the 1, this should be x to the 0. And then this, we have the this term, the second derivative term, and then we have the third term, or the third order term. And then we just plug it in based on what we found. So, oh, there we go, finally zoomed out. So what do we get? If we plug in, we basically plug in 1 into all the f values. So it's going to be 1, or 1 divided by 0 factorial times x to 0 plus 1 divided by 1 factorial x plus, let me write it here, 1 divided by 2 factorial x squared plus 1 divided by 3 factorial x cubed. And I guess the pattern emerged here that the next term will be 1 over 4 factorial x4, and the next term will be 1 over 5 factorial x5. So now we have that. Let's simplify through and just make sure we get a simplification form, or a simplified form. We get 1 plus x squared divided by 2 factorial plus x cubed divided by 3 factorial plus x4 to the, or 4 factorial. Okay. Now we have that. Our next step is to find the nth term with this pattern. So given this new index n, this is different from this again. So it's not similar to this n I'm talking about. This is a new n, and it's 0, 1, 2, 3, 4, 4, and then that means the nth term must be, for n equals, well, the index is n now. It's going to be x to the n minus n factorial. So that is the infinite series. N equals 0 to infinity of x to the n minus n factorial. And since x or e to the x is defined for all x's, this is for all, this is equal to e to the x for all x. And that's the second result. So this is the second one you must know. Let's move on to the third one. The third one. This one we've seen many times before, it's sine of x, but now we're going to actually show the general form and all that. So let's begin. Let's see. So I want to make the table again, the 3-column table. This helps for organization. If you really wanted to, and you can do this without the table, you can, but I'm just showing this just to show every step by step. So the zeroth derivative of sine is sine, so that means we just fill it in, cosine, negative sine, and negative cosine. And then if you evaluate it as 0, this is 0, 1, 0, negative 1. Okay? So now we just write the first couple terms. So I'm just going to do this. I'm going to skip one step. I'm still going to write the formula out because I feel like it's helpful, especially when you're starting to learn it. Now I can just plug it in. So the zeroth derivative evaluated as 0 is 0 over 0 factorial x to the 0 plus the first derivative at 0 is 1 divided by 1 factorial x. The next term is 0, so 0 over 2 factorial x squared. And the next term is negative 1 divided by 3 factorial x cubed. And simplifying through, since 0 appears on the numerator, this goes to 0 and this goes to 0. So in all, we're left with x minus x cubed over 3 factorial. If we were to continue this pattern, we'll see that this will lead to a 0, right? This is a type of sine. And then we repeat the process over, so it's going to alternate sign from 1 to negative 1 to 1. So that means it will be this, and then this, alternating signs and increasing by odd values. So we have this. What is the nth term? So now this is our nth, this is our n equals 0. This is the different index, 1, 2, 3. How do we relate these exponents to these n values? Well, notice that this is, every odd number can be represented by 2n plus 1. So if I plug in 0 here, it should be 1, and that appears here. If I plug in 1, it should be 2 times 1 plus 1, which is 3. So this 2n plus 1 is the exponent. And then it alternates sign, so we want to add a factor that changes sign as n increases. And then since it's also increasing by odd factorials, it should be 2n plus 1 in parentheses factorial, and this is the nth term. So then in all, the infinite series from n equals 0 to infinity of this is equal to sine of x. And this one is for, again, all real x. So that's this one. Very simple. Now we move on to number 4, the fourth one that you should know. And this one's related to sine, really closely related because it is cosine. So, like always, we're going to start with the table. And this one, and we're just going to start filling it in. 0, 1, 2, 3, 4, and then we just do this cosine, negative sine, negative cosine, sine, and cosine. Now we just fill it in. This is 1, 0, negative 1, 0, 1. Okay, now let's fill it into the Maclaurin formula, or Maclaurin series formula. And I'm always going to write it down just to help remember it. X to the n. And now I'm just going to fill it in right now instead of writing the first couple terms. So the first term is 1 divided by 0 factorial x to the 0 plus, and then 0 divided by 1 factorial x to the first plus, negative 1 divided by 2 factorial x squared plus 0 divided by 3 factorial x cubed. And then the last one that we're going to look at is this. Before we see a pattern emerge, we're going to simplify. Any term with a 0 on the numerator will cancel. This will be 1, so that's going to start us off. It's going to be minus x squared divided by 2 factorial and plus x to the 4th divided by 4 factorial. And then if you were to logically add more terms, it's going to alternate signs and increase by even powers. Notice that the cosine will increase by even powers, this being x to the 0, technically. And the sine will increase by odd powers, so they're really related to each other in that they just alternate signs, but one's even and one's odd. So now we start with this new index 0, 1, 2, 3, and our goal is to find the nth term. The nth term, so we're thinking about alternating, so this term will have to be included. We're thinking about even powers, so even, if 2n plus 1 was for odd, then even should be 2n. And we can check this. The 0th term should be x to the 0, the first term should be x to the 2 times 1, the second term should be x to the 2 times 2. So this makes sense. And that means the factorial should also have that same form. So now we can write the Maclaurin series for cosine, which is this form. Which is equal to cosine of x, and it's valid for all real numbers. All real x, I'll say instead. All real x. Okay, moving on. So we are going to go to the fifth one that we should know, and let's use this color, light blue. 5. We're going to be looking at the natural log of 1 plus x, so a natural log example. So like always, we're going to make a chart. And let's continue on with 0, 1, 2, 3, 4. And we can take the derivatives really easily of natural log. Oh, why did I switch to red? The natural log of 1 plus x. The derivative is 1 divided by 1 plus x. The derivative of this is negative 1 divided by 1 plus x squared. And then we get, we bring the power down, so it's 2 divided by 1 plus x cubed, and then we get negative 6 divided by 1 plus x to the 4th, and we evaluate it at 0. So natural log of 1 is 0. This one is 1, this one is negative, what is this? Negative 1. This is 2, and this is negative 6. Okay, now we go to the Maclaurin part of it, the infinite series from n equals 0 to infinity of this form. And what do we get? We get 0 over 0 factorial x to the 0, okay, plus 1 divided by 1 factorial x, plus negative 1 divided by 2 factorial x squared, plus 2 divided by 3 factorial x cubed, plus negative 6 divided by 4 factorial. Let me write it down here. Plus negative 6 divided by 4 factorial x to the 4th. And we see this term cancels out, so let's simplify a bit. X minus 1 divided by 2x, or let me do it like this, x squared divided by 2 factorial, plus 2x cubed divided by 3 factorial, minus 6 divided by 4 factorial x to the 4th. And we can even simplify further with this factorial because something appears on the top. So let's do that. The way I'm going to do is I'm going to start with this term right here. So the way I can rewrite 6 is actually 3 factorial. And the way I can rewrite the bottom is 4 times 3 factorial because that's what a factorial is. So now this can cancel out with this. So I'm left with x to the 4 divided by 4. Similarly, if I were to do the same thing to here, this would be 3 times 2 factorial. This cancels out with this. And then the same thing happens here. This is 1 factorial x squared divided by 2 times 1 factorial. So, and then I can just add this x here. So what do I get in all? I get x minus x squared divided by 2 plus x cubed divided by 3 minus x4 divided by 4. And then logically x5 divided by 5. So now we can continue on. Let's find 0, 1, 2, 3, 4. But when I do this, notice that this is always 1 greater than this. This is kind of weird. I kind of don't want to work with that. I kind of want to make it easier on myself. I can change the index starting at 1, and that's how I'll solve this annoyance or this problem, because if I do 0, then the Maclaurin series that represents it has to have taken into account that it being less than 1. So if I start at 1, that's fine, because I can just start the index at 1. But we just have to keep that in mind. So what is the nth term? Because of this rule that I made, it's going to alternate. It's going to be n minus 1 because of that rule that I implemented. If we plug in n equals 1 here, it's going to be 0, it's going to be even. If I plug in 2, it's going to be odd, so it's going to be negative, and that is represented by that n minus 1 factor. And then it's just x to the n divided by n. Since we found the nth term, we have to, now we can write the Taylor part, or the Maclaurin part of it. Notice that I started at 0, but no, I actually have to start at 1 because that's what I said here. So if I start at 1, this is true, but if I start at 0, it's not true anymore. So you have to keep that in mind, because you might accidentally forget that. And this is equal to natural log of 1 plus x, and then the interval is for all, for all x between these values. And notice that this is not an equal sign or less than or equal sign, it's just a less than symbol, and then this one's a less than or equal to symbol. So that's the fifth result. Let's move on to the last one. This is the hardest one. Not because of the Maclaurin part, but actually because of the derivative part. So we're going to take a shortcut with that, because I don't want to spend the whole video doing quotient rule. And you'll see exactly what I mean by quotient rule when we start. So again, I get the 3 parts that I need, and then I do this. So 0, 1, 2, 3. Okay. What are the derivatives? So this is tangent. This is 1 divided by 1 plus x squared. This is negative 2x divided by 1 plus x squared to the negative, or to the squared power. And then we would have to use the quotient rule here, but I'm just going to say something, right? Whatever the derivative is at that, and you can use your calculator actually to compute this. Just plug in this and put in numerical derivative x equals 0, and you should get what you're looking for. But I'll just tell you these values are 0. This one is 1. This one is 0. And then this third term, where n equals 3, is actually, it's negative 2, and then we would continue this down. But I'll just show you the pattern here. So now we just continue on, n equals 0 to infinity of this form, and then we continue. So what do we get? We get 0 over 0 factorial x to the 0 plus 1 divided by 1 factorial x to the first power plus 0 to the 2 factorial, or not 0 to the 2 factorial, 0 divided by 2 factorial x squared plus negative 2 x cubed divided by 3 factorial. And let's see what we get. Okay, we get 0 plus, these are 0, so actually I'm just going to cancel those out like this. It's x minus 2x and then 3. So we can simplify this further, and what do we get? We get, let's see, this is the same as, how can I say, 2 factorial. So it's kind of very similar to the other one. This is the same as 3 times 2 factorial, and this is equal to that, x cubed divided by 3. And the pattern here that emerges, if you want to continue this down, you could, but I'll just tell you the pattern. It's going to be like this. This is the pattern. It's going to increase by odd numbers, and it's not going to be factorial on the bottom. In fact, it's just going to be the plain number. So now the next step is to write the n terms, all the terms. So for n is equal to 0, 1, 2, 2, 3, 4. What do we get, right? So let's think about this. If n is, let's look at a random term. This is odd, so we're thinking about 2 plus 1 kind of thing. So it's alternating. There's a 2 plus 1 factor here, or 2n plus 1. And then it's divided by the same number, so it should be 2n plus 1. Notice that there's no factorial here, so it's different from the sine one is different from the sine one because there's no factorial. So this is n. So now we continue on. We want to find the Maclaurin part of it. So that's very simple. The Maclaurin part is the infinite series from n equals 0 to infinity of this alternating term times x to the 2n plus 1. This ensures it's an odd number, and this ensures that the bottom is also an odd number. And this is precisely equal to the inverse tangent. And this is valid for this interval, and that's the result. So we found 6 of them in total, so these are all 6 of them. Let me zoom out. We actually did a lot. I don't know what this was. I think this was from a thing that I did earlier, but that's fine. This is all of them. You'll see it's a lot of work just to get to 6, but now that we did it, you just have to memorize these. Let me box this one for completeness. Okay, so these are all 6 of them that you should know. Yeah, it took a lot of work just to get 6 results, but we got to them, and with this we can actually find a lot more Taylor or Maclaurin series just from these facts, because all we have to do is change the input and we get our result. So with these 6 Maclaurin series that you must know, just remember the indexes starting at x equals 0. This is the only one that starts at n equals 1. And then I would also maybe note the area it's defined on. Most of them is for all real x. Only some of them have a specific interval it needs to be a part of. But other than that, that's all for this video.